In a single span beam, we initiate the reinforcement process by addressing the lower section of the beam. The bottom reinforcement is provided to counteract the bending stresses and prevent the formation of cracks in the region of the beam that's vulnerable to tension. These bottom bars extend into columns and feature 90-degree hooks at their ends for secure anchoring. If the design calls for it, additional bottom bars can be added to the span, excluding 1/6 of the span from each end of the beam or as specified by the design. Following that, we provide top longitudinal bars which also extend into columns and incorporate 90-degree hooks for anchoring. Top reinforcement is vital for resisting bending stresses at the supports of the beam. If necessary, additional bars are provided, usually up to 1/4 of the span from the face of the column or as specified by the design. These top extra bars are placed in a lower layer when there is insufficient space for them in the top layer. Following that, we provide shear reinforcement in the form of vertical stirrups throughout the span of the beam. Stirrups are critical for withstanding shear stresses and keeping the longitudinal reinforcement in place. Stirrups are typically closely spaced near the end zones of the beam where shear forces are most significant. However, in cases mandated by the design, closely spaced stirrups can be distributed along the entire span of the beam. In this video, we are going to discuss how to calculate the bar bending schedule of a single span beam. Let's illustrate the process with the help of an example. We need to prepare the bar bending schedule of a beam whose width is 230 mm, depth of beam is 450 mm, clear span is given as 3000 mm, the clear cover is 25 mm, and development length is 40 times the diameter of the bar. For longitudinal reinforcement, we have 4 categories of bars to calculate. 2 number of bottom main bars of dia 16 mm, 1 number of bottom extra bar of dia 20 mm, 2 number of top main bars of dia 16 mm, 1 number of top extra bars at each end of the beam with dia 16 mm. For shear reinforcement, we have 8 mm stirrups placed at 100 mm center to center at end zones and 150 mm center to center in the intermediate zone of the beam. First of all, let's do the calculation of bottom main bars. The diameter of bars is 16 mm and the number of bars is given as 2. Cutting length of main bars will be clear span plus twice development length minus 2 times 90-degree bend reduction. Clear span is given as 3000 mm, development length is 40 times d, and 90-degree bend reduction is 2 times d, where d is the diameter of the bar. On substituting these values, the cutting length of bottom main bars will be 4216 mm. Cutting length in meters will be 4.216 meter. Total length will be equal to cutting length into number of bars and the total will be 8.432 meter. Unit weight of 16 mm bar will be 5 square upon 162.2, which will be equal to 1.58 kg per meter. Total weight of the bottom main bars will be equal to unit weight into total length. Unit weight is calculated as 1.58 and total length is 8.432. On substituting these values, total weight of bottom main bars will be 13.32 kg. Now, let's do the calculation of bottom extra bars. The diameter of bottom extra bars is given as 20 mm. Number of bars is 1. Cutting length of bottom extra bars will be equal to clear span minus clear span upon 6 minus clear span upon 6. Clear span is 3000 mm. Therefore, the cutting length will be calculated as 2000 mm. The cutting length in meters will be 2 meter. Total length is equal to cutting length into number of bars. Cutting length is 2 and number of bars is 1. Total length will be 2 meters. Unit weight of 20 mm bars will be 5 square upon 162.2, which will be 2.47 kg per meter. Hence, total weight of bottom extra bars will be unit weight of bottom extra bars into total length, and the total will be 4.94 kg. Again, let's do the calculation of top main bars. The diameter of top main bars is given as 16 mm. Number of bars is 2. Cutting length will be equal to clear span plus 2 times development length minus 2 times 90-degree bend reduction. Clear span is 3000 mm and development length is 40 times d, where d is equal to 16 mm. On substituting these values, Cutting length of top main bars will be equal to 4216 mm. Cutting length in meters will be 4.216 meter, and total length will be equal to cutting length into number of bars, which will be equal to 8.432 meter. Unit weight of 16 mm bars is 1.58 kg per meter, and total weight will be unit weight into total length, which will be equal to 13.32 kg. Now let's do the calculation of top extra bars at both right and left end of the beam. The diameter of the bars is 16 mm and number of bars at each end is 1. Cutting length of top extra bars will be equal to clear span upon 4 plus development length minus 1 times 90 degree bend reduction. Clear span is 3000 mm. Development length will be 40 times 16 mm and 1 times 90 degree bend reduction will be 1 times 2d. On substituting these values, cutting length of top extra bars will be 1358 mm. Cutting length in meters will be 1.358 meter. Total length will be cutting length into number of bars, which will be equal to 1.358 meter. Unit weight of 16 mm bars is 1.57 kg per meter. Total weight will be unit weight into total length, which will be equal to 2.13 kg at each end of the beam. Therefore, the total weight of top extra bars will be 2 times 2.13, which will be equal to 4.26 kg. Finally, let's do the calculation of stirrups. The diameter of stirrups is 8 mm. For zone A, the spacing is given as 100 mm center to center. Number of bars will be clear span upon 3 plus clear span upon 3 upon spacing plus 1. Clear span is 3000 mm. Spacing is 100 mm. Therefore, the number of bars in zone A will be 21. For zone B, the spacing is given as 150 mm. Number of bars will be clear span upon 3 upon spacing, which will be equal to 6.6, say 7 bars. Total number of stirrups in zone A and zone B will be equal to number of stirrups in zone A plus number of stirrups in zone B, which will be equal to 21 plus 7. The cutting length of stirrup is given by the formula twice A plus B plus 2 times 10D minus 3 times 2D minus 2 times 3D, where A is the center to center distance between the extreme vertical bars of the stirrup along the width of the beam, and B is the center to center distance between the extreme horizontal bars of the stirrup along the depth of the beam. A will be equal to width of beam minus twice clear cover minus 2 times D by 2. Width of beam is 230 mm, clear cover is 25 mm, and diameter of stirrups is 8 mm. On substituting these values, A will be equal to 172 mm. Similarly, B will be equal to depth of beam minus twice clear cover minus 2 times D by 2. Depth of beam is 450 mm, clear cover is 25 mm, and diameter of stirrups is 8 mm. On substituting these values, B will be equal to 392 mm. It shall be noted that 10D is the hook length where D is the diameter of the stirrup. 2D is bend reduction for 90 degree bend and 3D is the bend reduction for 135 degree bend. On substituting these values in the equation of cutting length, we get the cutting length of stirrups equal to 1192 mm. Cutting length in meters will be 1.192 meter. Total length of tie bars will be equal to number of tie bars into cutting length of each bar. Number of tie bars is calculated as 28 and cutting length is 1.192 meter. The total will be 33.37 meter. Unit weight of 8 mm ties will be 0.39 kg per meter. Total weight of stirrups will be unit weight into total length. Unit weight is 0.39 and total length is 3.37. On substituting these values, total weight of stirrups will be 13.1 kg. Total quantity of steel will be weight of top bars plus weight of bottom bars plus weight of top extra bars plus weight of bottom extra bars plus weight of ties. The total will be 49 kg. So this was all about this lecture. If you want the manual calculation PDF and the Excel sheet of this topic, you can check out the link in the description box of this video. Thank you.